Our smartphones are truly marvels of engineering. Did you know that inside your smartphone, there could be up to 1,000 chip capacitors? Each one may be composed of hundreds of miniature stacks of complex layers, and yet these capacitors get smaller and smaller all the time. These tiny, multi-level chip capacitors, or MLCCs, are actually engineering marvels in their own right, requiring amazing process controls and materials engineering. Today, we get to learn more about these amazing components from an industry expert. Welcome to Tech Chat, sponsored by KYOCERA Electronics, where we chat with experts about the latest technical innovations in the electrical engineering industry. On today's Tech Chat, we are joined again by Ron Demko, a Components Fellow at KYOCERA AVX. Ron, welcome back to Tech Chat.
Thank you, Dale. I appreciate that. It's good to be here.
So, Ron, why don't you tell us a little bit about yourself, including what exactly is a Components Fellow, and introduce today's topic?
All right. Well, I've been working at KYOCERA AVX for approximately 40 years, and I've got a BS in electrical engineering. I do a lot of design work and experiment work on the home. I've got a ham radio license. Luckily, I've worked all over the world and even operated from some different locations around the world. So today I'd like to talk about miniature high capacitance MLCCs. This is an important topic, and it's important because, well, the most obvious thing is that the end product sizes are dropping, but within those end product sizes, the IC rail voltages are also dropping and system complexity is increasing. So that combines to create a perfect storm and a need for miniature and high CV multilayer ceramics.
Well, that sounds great. I'm ready to jump right in with you.
Well, the goal of today is to update end users on some high quality solutions for end product designs. What we're going to do is very briefly look at construction and some miniaturization efforts. We'll talk about the important performance parameters of some of the ceramic capacitors that are miniaturized. We'll look at a circuit example, look at a roadmap, and then have a quick summary.
Yeah, I'm looking forward to it. As a double E, I've obviously used capacitors countless times, but I really don't know anything about how they are constructed. So I'm looking forward to getting a peek inside and also the roadmap. But before we dive into those technical details, can you give us a little background on your company?
Sure. Well, and the background is really interesting because the innovation from manufacturing is really what got us to the point of being able to make some of the best miniature high CV ceramics out there. So KYOCERA started manufacturing MLCCs in 1971. AVX was around 1972. And KYOCERA had their first major expansion on MLCCs with the Cuba plant in 73. AVX had that in 77 and 79 between El Salvador and Northern Ireland. And then in 1990, we were lucky enough and merged up with KYOCERA, became a wholly owned subsidiary in 2021, and now integrated into a division of KYOCERA. So we're very lucky. We have the ability to join process engineering and design and R&D, and we get an exponential return on our capability in creating these new types of products.
And I would think with 50 plus years of development and manufacturing experience, I think it's safe to say that you guys know a thing or two about MLCCs.
Yes, that's true. There's an awful lot of interesting quirks to the process and ways that you could optimize design and processing.
All right, Ron, take us behind the scenes then into how these capacitors are made.
Okay, well, we'll look at this in a very high level view. MLCCs are very complicated, and it's good to take a look at the process here, and then we'll apply that to what we're going to talk about the rest of the presentation. So we start off with a raw material. That raw material has to be created in certain sizes and compositions, but that's a very unique and important part of the overall design of this component. That material is then cast into a tape. That tape is almost like a piece of paper in its thickness, and we will then print electrodes on top of that ceramic tape. The component is then stacked vertically until we get the right capacitance value and dimensions, etc. It's pressed into a monolithic structure and cut into individual components. They could be the larger parts or the smaller parts, but they're all diced up into these little miniature components from that pressed wafer start, so to say. We then fire the parts to make them a monolithic block. We'll put a termination on them and plate the parts. Of course, there's lots of testing and QC checks that we don't talk about, and quite a few other things that occur, but those are probably the big 8 steps that are worthy to note.
So is that stacking, is that like multiple prints to stack those up, or are you like cutting out individual devices and then stacking them together?
Yeah, we'll stack the whole plate at a time. So we take a piece of ceramic, we print the electrode on it, we bring another piece of ceramic on top of it, print the opposing electrode, and keep building up in a vertical fashion like that.
So now that we've seen how these MLCCs are made, let's look inside the finished product.
Yes. Okay, well, it's really important to look at what's going on inside of these parts. Now, as we talked about before, the ceramic actually isolates the metal. There's a metal ceramic metal structure that goes vertically, as you can see in the cross section of this device. The terminations have a copper layer followed by a nickel, and then commonly a tin plating on the outside. And what you'll find in the ceramic capacitor is that there's an effective area, and that effective area is the yellow portion where the electrodes overlap. That gives us the actual capacitance of the device. Now, what's important to note, the dielectric, of course, is very important. It separates the two opposing metals, the two electrodes. It provides most of the electrical characteristics of the component. But that ceramic also encapsulates those electrodes from the outside world. And you can see that in the bottom right-hand corner where there is some margin where the electrode set or the electrode stack is isolated from the outside world. And that basically is how we create a multilayer ceramic capacitor. Now, the capacitance is equal to some dielectric constant, which varies based upon the type of material we use. It varies upon the active area. There's the number of laminated stacks that we have, and then the ceramic thickness. So there's the way that we achieve capacitance with the formula on the top center. Essentially, you want more electrodes and thinner dielectrics with a good, stable dielectric.
And Ron, what is the range of the laminating layers that you'll see in one of your modern MLCCs?
Well, we've got a cross section a little bit later on that shows 500. So many hundred is not uncommon, and it really depends upon the type of capacitor that we're looking at.
Okay. So you mentioned here smaller cap sizes. How small are capacitors getting today?
Well, it's a multilayer part could be as small as a 008004, which is 0.25 millimeters by 0.125 millimeters. It's really teeny. And in fact, those are so small, they could be encapsulated inside of IC packages and a variety of other things. They're exceptionally useful. And if you look at what the transition from larger case sizes to smaller case size buys us, as you can see in this chart, first off, we could reduce the mounting area dramatically. So if you see the 0805, we'll call that a mounting area of 100%. And as you go down in case size, we could drop the mounting area of that just dramatically. So we can go on down to approximately 4.2% of the area from an 0805 to a 008004. Now, there's massive weight reductions that are very important in our world of portable electronics and flying drones and wonderful things like that. And there's also an interesting impact where we may be using 100 0603s, but changing to 0402s could give us a dramatic board reduction. And you could see that we could change by 54%. Or you could also increase the number of 0402 capacitors to be used within that same area. And you could see further reductions going to 0201s, etc. And as we have cell phones that might have 1,000 components, 1,000 ceramics on them, 1,000 MLCCs, it's really important that we get to these miniature case sizes.
Yeah, the progression here is pretty astounding. I honestly hadn't ever heard of 008004 before. So That's it's a new one to me, and that's really small because I've tried to pick up 01005s before, and it's pretty hard.
Yes, it's very difficult. You know what? This is really interesting though, because this slide really summarizes that we have high CV ceramics, and we're either going to build smaller case sizes or we're going to have higher cap in the large case sizes, and that's really important. It covers both ends of the market.
So, is there a next step in this series, the next smaller size being planned already?
I'll never say never, but I think we're getting to the point where it might be pretty optimized for end applications. Now, what we see here is a cross section of an 0402 22 microfarad component. It has over 500 layers, and each layer is approximately 1/100th of a human hair diameter. On the left, you can see the BT, that's our ceramic, that's the barium titanate, and the lighter lighter line is actually the electrode. That happens to be a nickel electrode. So this is really interesting. This is the cross section of that small part, the 0402. And you could also see that there is a lighter area. That's the active area. Remember prior we had that highlighted in yellow? That's
Mm.
the active area which actually gives us the capacitance within the device.
Now, the process control has to be just absolutely incredible for these capacitors, since the slightest imperfection could cause a device failure.
Yes, that's absolutely true. And there's process control in many different ways. We have to worry, of course, about the material purity. We have to worry about the ceramic laydown, also the nickel laydown. There's so many things that we have to worry about. Probably there's not enough time in the whole discussion here. But then there's also mechanical things that we need to be concerned about. The fact that we need the stack to be relatively straight, so no electrode enhancements or no corona areas are occurring, etc. It's really complicated, but it's well controlled, and we've got a good handle on it.
Now, the thinner dielectrics are great for getting more capacitance, but that makes it harder to prevent voltage breakdown because the electric field strength gets higher.
Yes, that's true. But there's improvements in the ceramic itself where we have smaller grain size, different composition. That's one way to reduce the E field stress per dielectric layer. And then the other thing is there's just an inherent reduction or trend to reduce the rail voltages on semiconductors. So, when I started, we were perhaps at 12 volts. Now, pretty much when I started engineering, and now here we are sub 1 volt. So, there are trends that kind of are going our way that allow us to pack more electrodes in there with a lower applied voltage on the part and still get incredibly high reliability.
Oh, that makes perfect sense. So you kind of talked about it briefly, but you have to improve these dielectrics to meet the new challenging requirements for these applications.
Yes, that's absolutely true. And most of the capacitor's performance characteristics are a direct result of the dielectric. Now, here, what we're showing is three standard dielectrics that are available in these miniature components. And there's more dielectrics that we could talk about, but let's talk about the most three common ones: the CLG NPO, the X7R, and the X5R. What we're showing is temperature stability across temperature, and this would be typical of what the electronic um, organizations across the world have for the typical requirements. X5R, of course, is the most highly optimized dielectric for large capacitance MLCCs. The X7R is a great general purpose part for intermediate type of applications. And then the NPO would be everything from optics to RF and timing. Essentially, between these three dielectrics, you have the passive glue that could connect any IC chipsets to any other type of structure, whether it's another IC, an RF amplifier, an antenna, some form of IO, even energy harvesting. All these three dielectrics here will give you the tools to connect to anything.
So then you've got trade-offs for the designers. I take it that they can trade off temperature stability for better RF performance and that kind of thing.
Yes, that's right. That's absolutely true. And there's other dielectrics that are out there. But the key point behind all these dielectrics, and whether they're on this chart or even off of it, we've made great improvements on them, whether it be the inherent composition or the stability, either with voltage or time or with temperature. All of that impacts reliability and end product. So things have gotten dramatically better, even though they're much smaller, with possibly even higher electric stresses. It depends upon the design, but things are more reliable now than ever.
Just the miracles of modern engineering and process and manufacturing improvements are incredible.
Yes, it's beyond belief. The closed loop processing is wonderful. Vision is wonderful. All of this is just amazing. Looking back at it 40 years ago when we didn't have any of it.
Yes.
So we've improved dielectrics, and those improved dielectrics have given us better electrical performance. And that's incredibly important for the end user. Now, it's key to know that not all ceramic capacitors are equal. If we look at this 0603 47 microfarad part, which is rated at 4 volts, we're looking at a KYOCERA AVX part on top, the blue part, versus a competitor part. And what we're looking at on the left-hand chart is the effect of the DC bias on the capacitor. And you can see as you bring the bias voltage up on a capacitor, its value drops. Now that's a standard phenomena that's across all of the manufacturers out there. It's quite important, though, that our dielectric has the least amount of drop than any of the competition out there. And that's significant because if we're building like let's go back to an old bulletproof 78L05 regulator. I mean, we need to know a certain amount of capacitance. We need a minimum capacitance that's out there. And it's important that AVX KYOCERA group has the better, more consistent capacitance that you could expect as a designer. Now, the same situation is true across temperature, where KYOCERA AVX parts have more stability across temperature. We have less of a temperature loss. All of these are additive, by the way. So for the designer, this gets incredibly important. But the bottom line is the optimized dielectrics, which we have, yield more stability in actual circuit situations.
Yeah, you're going to get a real surprise there if you've designed in your 47 microfarad capacitor, but now you're running it at a 4-volt bias and you're getting a like 15 microfarad capacitor. That's going to change the performance of your circuit and not going to be pleasant.
Yes, it could be devastating. We've dealt with so many engineers that have experienced that. I'll have to say that this isn't at least something that we were taught in engineering school. Of course, that was so long ago. It holds very little merit to what's going on today. But likewise, the engineers that I'm talking about today that are coming out, they really don't expect or assume this type of performance. So many times you get burned. Once you get burned once, you'll always remember DC bias, temperature variations, etc.
And you mentioned that these are additive. So in that figure on the right, so that is at a 4-volt bias and then across temperature. Is that correct?
The one on the right is a 2-volt application on that device. So as we change voltages, that also will go up and down. Now, what we're looking at here is the general improvement of the volumetric efficiency in terms of microfarads per millimeter. And you can see that, of course, as time goes on, we're improving that capacitance density. And it's improved by basically having a smaller grain size and a higher K factor within a given amount of thickness. One thing that we're showing here is that we're getting to remarkably high amounts of capacitance, even in the miniaturized devices like 01005. We're going to be approaching 1 microfarad. That's under development. And there's very key values which are currently available out there. And those are also shown in the graph. The key point to all of this, though, is that there is a very large amount of effort being placed on getting high amounts of capacitance in the whole spectrum of case sizes that are out there. Now, there's another impact that small case sizes have, and that's actually upon the inductance which they present to the end circuit. And as you drop the case sizes, the inductance drops. So that actually allows the capacitor to work at a broader frequency spectrum relative to higher inductant parts. So there is a subtle advantage as well, as you see with time, that these smaller devices will offer, and that's lower inductance and therefore a little bit more circuit efficiency.
Yeah, these are really tiny engineering miracles, right? It's incredible design, the materials development, the manufacturing process. There's a lot going on inside there.
Yes, that's true. It's interesting that I actually have worked a little bit with semiconductor world early on, and of course the advantages or the progress made in semiconductors has been startling, and now we're down into to 14 nanometers below whatever, but remarkable gains have occurred in the world of semiconductors. But when you look at it, there's been equally remarkable progress in the world of passives, and these types of improvements in ceramics are very, very interesting. And I'll tell you a quick story. When I started, we were first trying to create a surface mount capacitor, and we were failing at approximately 40 years ago to create a 1210.1 microfarad component, a 1210.1. So
Hmm.
look at the progress we've made. It's just been outstanding.
Yeah, it's really exciting to look back and to see that growth and really, yeah, the semiconductor industry gets a lot of the press, but if the rest of the component world didn't come along with it, then we would have run into different bottlenecks.
That's true. And now I think it's actually probably fair to say that semiconductors are so advanced and they're so powerful that passives are beginning to become the limiting portion of their performance. So we need high CV devices, which are low inductance, to be around the voltage rails. We're going to need advanced devices for AC coupling, etc. Without those semiconductors are going to have to throttle back their speed and functionality. So we're just at the point where I believe the passives and ceramic capacitors and tantalums and even electrolytics in particular are getting their due amount of press. They suddenly are now some of the gating elements in the design.
Yeah, that's really interesting. Well, you mentioned here on the right some of the advanced products you have in development. Can you provide us some insights into your product roadmap for MLCCs?
Sure. Basically, we could say that we're increasing the amount of capacitance in any given case size, as you could see here on this chart. We're working on an expanded voltage offering. Some of these circuits will have certain needs for different levels of voltage, of course, depending upon what type of end structure IC that they're used in. And in all cases, we're working on improved reliability, which is already outstanding, but I think we could take it up even another level. So we're seeing a tremendous improvement. And of course, this is just the X5R roadmap. There's equivalent roadmaps for all other dielectrics, which are equally impressive. X5R, though, we could probably say is a good general purpose high CV part out there. So we felt this would be most representative and useful to show the engineers.
And what does the abbreviation RV stand for in your chart?
Rated voltage.
Okay. And what's a key product?
Well, it's going to vary by case size. In many cases, 201 might have a 4.7 mic at 6 volts, or a 2.2 at 10 volts. The 0603 that has 47 mics as a very big runner, so that's quite impressive. So these are numbers that are very useful in everything from power trees to optics and even some regulator circuitry out there, and certainly more. But it's amazing that we can get such amounts of capacitance in these small components.
It really is.
Well, one of the things that is not really paid enough attention is the amount of weight reduction that we get in going to these small components. It's very easy to see that we're dropping down our mounting ratio by 90% or by 50%, whatever. It's quite easy to see that, but less evident is the weight reductions. And this has become very important in the world of course, portable electronics, but also in the world of drones that I dabble with and do some work and trying to design things. So we're seeing that we can suddenly now start packaging these types of components with almost no impact to end system weight requirements. And even in the world of low Earth orbit satellites and LEOsats and even ThinSats, the CubeSats, things like that, some of them, the low priority devices, are using non-flight grade components because of the flight characteristics of the satellite, and they're receiving quite a bit of benefit from these reduced component sizes. Now, I will say, though, in the world of high reliability components, space grade type components, they're also seeing dramatic reductions in the case size and the weight and the volume and mounting areas of components. So this type of weight and size trend is actually occurring across all aspects and all end markets of passive components, particularly MLCCs.
Yeah, I think one of the kind of the hidden advantages you might have is the improved reliability inside my smartphone. If I drop it and the capacitor is much, much lighter, the shock when it hits the floor is going to be less. And so you're not going to be shearing off these components.
Yes, that's absolutely true. They have tremendous reliability in shock and vibration environments.
Yeah, and that's got to be obviously great for satellite launches as well.
Yes, I'm amazed to see the types of oscillations and shock profiles that those components have. And of course, those are mostly different grade parts, high rail space grade parts. But as we've said before, that those are going to go from the larger case sizes down into miniatures as well. So yes, small size is going to make all the difference on shock and vibration, even thermal cycling, things like that.
Oh yeah, good point.
Another area that it's really interesting what these small capacitors are building us or giving us is the ability to create nano circuitry. And what we've done here is we've excerpted some things from Texas Instruments. They've got a really neat nano DC to DC power converter product line, and it's basically a DC to DC microconverter. It could get you 1 amp out, but they use ultra miniature components. And it's neat to say that the capacitors are no longer the limiting size of this end system. You could see some very unique packaging of that device on the right hand side and some photos of it on the left. It's a very sleek, easy to use design. And as we said before, it's wonderful that we could state that we are no longer the limiting portion of that. Now, likewise, we've done other studies, and we could look at even energy harvesting ICs. And there again, we could say that we are no longer the limiting case size in a variety of energy harvesting or even energy scavenging circuitry. So miniaturized ceramics and other miniaturized passives are having a tremendous impact upon how close they could be placed to the IC and how we could package the IC and the overall end use of that IC structure.
Yeah, and I've seen where they're putting them inside the printed circuit boards, inside the layers for some advanced packaging. There are all sorts of crazy things that are being developed now that these have become so small.
Yes, in fact, we've just introduced one of the first RF grade capacitors for embedding within structures. And I think ultimately this is going to be very important as we get to 3D semiconductors. There's going to be a huge need for different types of packaging of these passives.
I suspect you're right. So, Ron, why don't you summarize our discussion today for our audience?
Okay, well, great progress has been made in high CV miniature multilayer ceramics. We saw the process steps. The process itself has been improved greatly. And also dielectric improvements have really impacted the type of components that you could get. High CV parts are typically associated with X5R dielectrics. However, there are very advanced other dielectrics that we have alluded to, ranging from RF to general purpose, even extended temperature. Those dielectrics should be considered. So although they're not shown here, there's been exceptional progress in all of those different dielectrics. And we'd also like to say that 01005 parts and smaller in many different devices are now suitable for many different types of end applications. That's really key. And the use of MLCCs in power electronics has been shown. It offers improved ripple. And that's important as we get to lower power rail ICs. What we're going to need is much reduced ripple. And the way to get reduced ripple is to have a lower ESR on those capacitors for filtering, and that's exactly what we've done. So it's really a perfect fit with next generation ICs. And then we also had a quick recap of values and some future developments that are shown. And there's some other really interesting things that aren't shown. We hope that we could talk about those shortly, but the progress is really not stopping here, and there's quite some exceptional new types of components which are coming out. In the meantime, though, everything that we've got is going to be directly applicable to this set or this generation of ICs, as well as the next generation coming out.
Well, thanks, Ron. That was a lot of fun, and I definitely learned a number of interesting things today, and I think it will really benefit our All About Circuits audience.
Thanks, Dale. It's been a pleasure, and I hope to see you again.
Yeah, and if you're looking for more information on KYOCERA AVX, check out their products at Mouser Electronics, our sponsor for this Tech Chat. And a special thanks to our multi-level chip capacitor expert, Ron Demko, for taking time out of his busy schedule to speak with us today.